We'll get started. So it's a great pleasure today to have Professor Fernando Escobedo. Fernando is from the School of Chemical and Biomolecular Engineering. In fact, a colleague of mine since, 1997 or 1998, around there. Fernando is, has won a number of young career awards, the Camille and Henry Dreyfus Award, Alfred P. Sloan, NSF Career Award. More recently, he's been elected to a fellow of the APS, Computational Physics, and he's in College of Engineering. He's won a teaching award, as well as he's now the Marjorie Hart Chair of Engineering. So Fernando's has been doing some statistical physics and some beautiful calculations, and I think he's got some good math problems buried in a lot of his work, so I'll let him take over. And this is the bad, the ugly, and the good, or what is the order? Fernando.
Well, thank you, Paul, for this kind introduction, and thank you to everybody for coming. So in this talk, I'm hoping to show some of the work that my group has been doing in trying to engineer entropy in nanomaterials. And this is a work that has been done by three students, Umang Agarwal, Michiel Kadilkar, and Vikram Thapar. And just in case, these three words, the good, the bad, and the ugly, refer to the entropy, not to the three students. Okay? Now, just to clarify again, sometimes when I say that I have a modeling group, some people get the wrong idea. They may think that we look like this. We don't. We look more like this. And in fact, these are not two of the students whose results I'm going to present today. And we do not model shoes or clothing, but we model some of these very interesting nano objects. And what we want to know is how is that they assemble at the micro scale. And those properties are going to translate in potentially very interesting applications. And as you can see, some things are particles, some things are polymers or biopolymers. And this is something I wouldn't tell the funding agencies, but sometimes the choice of problems is driven by things that we feel are beautiful. So in some ways, we are trying to capture this beauty by using the statistical mechanics. So in some ways, we are a modeling group in more than one sense. So first, I'll try to give a background on the role of entropy in designing materials. Then I will basically try to give you examples from one type of system, which are these colloidal particles that are space-filling or near-space-filling polyhedral, and because they may be sort of model self-assemblers. And then I will try to give you sort of the big picture as far as some of the methods that are needed and some of the challenges in looking at these problems. Now, I will only have time to tell you about thermodynamics, not kinetics. There will be a whole other talk. So just be thermodynamics, sorry. And then I will apply some of these methods to try to sort of find these design assembly rules for creating sort of new mixtures and compounds in solid phases. So to begin talking about entropy is perhaps a good idea to sort of cite Clausius' dictum that sort of summarizes the first and the second laws by saying that the energy of the universe is constant, but the entropy tends to a maximum. And there's probably nothing wrong with that, but as probably scientists and engineers, we oftentimes encounter energy as in the process of trying to convert one form of energy into another. And in that process, there's usually a loss of quality in this energy because entropy irreversibly grows. Right? And that's in fact what limits the efficiency of engines and power plants and so on. So there's something bad to that. But more generally, we tend to associate entropy with disorder, that for the most part is bad. And not only that, but this disorder is boundless. It's going to keep growing forever. And if we take this to the natural limit, then we can paraphrase Helmholtz, who said that the universe will end in a heat death. That will be the end of all physical phenomena, which I'm sure will be bad. So there is clearly this association of entropy with a destructive force in nature. Right? But again, I'm sure there are people here in the audience that know otherwise. That there are things for which entropy is useful. For example, people use depletion interactions or hydrophobic effect when they come to biomolecules. And in fact, there are very useful chemical reactions that wouldn't happen if not because some of the products are gas and hence have no high entropy. That's helpful. So we know this, but I think it's fair to say that when it comes to sort of thinking about designing new materials, entropy is the boss. And I think that that's justifiable. That should be, because that's in some ways our main knob to create new materials. It's being extremely productive. It will keep being very productive. What's not so good is that the role of entropy is often obscure or unappreciated, or to just think it's bad, so forget about it. So to try to counter some of this sort of bad blob that's going around about entropy, I've come up with my own aphorisms to try to sort of spin it in a more positive way. So my first aphorism tries to just summarize what I just said, saying that energetic interactions are designed intelligently, while entropic interactions are designed accidentally, which is meant to emphasize the idea that when you do this, you are really proactively doing it. There is a purpose to it, while when this happens, well, it's an afterthought. Now, there has to be a good, otherwise there won't be this talk. So one way to start looking at the good of this is to say that if we associate energy as being a selective force in nature, which it is, we can say that entropy is a creative force in nature. And in some ways I would say that that tension between specificity and diversity has been at play eons in nature. Probably happened in natural selection. And in fact, many people who do directed evolution or combinatorial search, they're in some ways exploring this diversity of entropy. But sort of rather than using this shotgun approach to find sort of good solution, good materials, we are more interested in looking at rational rules as to how you engineer entropy. Because after all, if you think about it, there are only two forces that you can use to design materials. Why relegate entropy to this sort of minor role? So to give a face to entropy, we should probably write Boltzmann equation that relates the thermodynamic idea of entropy with this microscopic quantity, which is the number of microstates, the number of configurations that the system can realize itself given some external constraints, which is the objective. And we recognize that there are different flavors of this entropy. We can talk about translational entropy. Mixing entropy will be one example, where we will realize that if we have two species, then if they mix, they're going to access more configurations, hence more entropy, so this is going to be favored as far as entropy. We can also talk about packing entropy, where if, for example, these particles are to be sort of confined, constrained in space, so rather than jam and have just one single configuration, they may actually order, if in doing so, like in this case, they can open up a little bit of a space around them so that they can rattle. By rattling, they will access more configurations, hence more entropy. In the case of sort of these rigid rods, you may also recognize that this system will have more rotational entropy compared, say, to this. But then again, if you increase the concentration high enough, it could be that under these conditions, the packing entropy can increase by alignment, and this increase in packing entropy can compensate for the loss of rotational entropy that you have in this system. And in fact, that's a way how entropic liquid crystals come about, like, say, pneumatic phases. And in the case of polymers, we can talk about conformational entropy, when again, we recognize that if the ends of this chain are more far apart, there will be less access to configurations to the chain compared to the case where the chain ends are less constrained, like in this case. And it's in fact sort of an interplay between these different facets of entropy and energy that will give us different solutions. And in fact, some of these solutions will be not possible if energy would be allowed to rule unchallenged. And one example of some of these mesophases, or these new solutions, are what we call mesophases. And to sort of illustrate what we mean by that, they are just phases with intermediate order. So for contrast, if you look at a typical crystal, like something like this, then you can argue that it will have complete positional and orientational order, positional immobility, and absence of flow. While in a typical liquid, you will have basically the opposite on all these criteria, like this. In the mesophase, you may have something like a plastic crystal or a liquid crystal, or segregated phases like in local polymers, or glasses, or gels in networks. And if you see these criteria, some will be yes, no, some will be partial. But in fact, is this intermediate combination of features that confers to these materials very unusual microstructures, very unusual properties, which makes them very useful in applications, as you can probably easily recognize. Now, in our work, we've been very interested in all these kinds of materials, but as I said, for this talk, I will just be confined to particles, so I will not be talking about polymers at all. Now, what would be the best way to try to sort of handle entropy? Well, it may be hard experimentally, but if you're using molecular modeling, a very nice trick is to just turn off all the energetic interactions. That will happen, for example, if you use hard interparticle potentials, which is what many people do. And this is something that we're going to do a lot in this talk, just because in that manner, if you think about it, any phenomena, anything you see that the system does, can only be blamed on entropy. So you know that energy is playing no role because there's always zero energy. So later you can add energetic interactions to have a more complete understanding of the system, but this is certainly a very useful decoupling. And because we're going to use hard interactions, this makes these sort of Metropolis Monte Carlo methods the most appropriate if we want to sort of do simulations in the system. Now, one of the motivations for looking into these particle systems is the idea that so many people have in their minds that if you now think about these objects, so they are like a new chemistry. In some ways, you can think of them as being superatoms, in the sense that at this scale, right, you can sort of do with them things that you wouldn't be able to do with the sort of conventional building blocks, conventional atoms. And at this scale, you can change anything you want, not only the size, but also the shape and the functionality in different axes of variability as shown here. And this idea is kind of sobering if you think about it, that any building block that you can imagine, that you can fancy, can be made. Maybe not tomorrow, maybe not cheaply, but if you show that it has useful applications, somebody will do it for you. And that opens the door, if you think about it, to many interesting questions, such as inverse design. And this also opens many unknowns, because we don't know how many of these building blocks will assemble, what kind of chemistry they are going to be able to do, what properties these assemblies will have. Now, in our own work, we have also explored a number of axes of variability. Some of them are shown here. But the examples I want to illustrate in this talk are basically for a family of particles that can be thought as having very interesting entropic bonds. And these are the so-called space-filling polyhedra, or some of them are near space-filling polyhedra, as they could be the superstars in this family of polyhedra. And there is a following that when these particles are put at the close packed density, they assemble into this very well-defined crystal, right? So it means that in their shape alone, these particles encode all the knowledge they need to go into this high-order crystalline state. And one way to sort of start understanding why is it that they can do this is by looking, for example, at the potential of new force. So what you will do in this case is, say, have a particle in the center and have a second particle that you probe at different distances and different orientations, and you see when at different distances you have overlap or not, and then minus the logarithm of the probability of no overlap. That's the potential of new force. That basically shows that we have a purely repulsive interactions as it should. But this is sort of the spherical average. In reality, of course, this interaction is orientation dependent. For example, if they come in this orientation, you can argue that the repulsion is more long-ranged. If they come in this orientation, it's shorter range. Right? Now, this idea of repulsion is really relative. I could also say that this is more attractive than that. Right? It's an attraction, it's a force that depends on the concentration, depends on what's the average spacing between these particles in the system. So at high enough concentrations, these orientations are going to, so the preference to certain orientations is going to guide the system into certain structures. So one could think about these interactions as being entropic bonds, which are directional in the same sense as, say, hydrogen bonds are directional. Now, you may think that cubes are rather uninteresting, boring. For example, if you look at cubes at the low concentrations, they're going to form this disordered suspension. By the way, I'm using different colors for the cubes just to make it easy to the eye to see that there are different particles. But they are all the same, they're all hard particles. And yes, they seem to be doing just nothing. While if you go to a very high concentration, say the cross-pack situation, then they're forming these cubic lattice. Notice again that I'm coloring layers so that it's easy to see in the order. But what may be interesting is what happens in between at intermediate concentrations. Because it may be that as this system goes down in concentration and goes into the isotropic phase, it may not melt all at once. It may be that it encounters a mesophase, not some phase with intermediate order, because after all, there are various degrees of freedom associated with the order of this crystalline structure. You have orientational order of the particles, interrelational order of the particles. So you may encounter something interesting. Now, do we? Well, this is what we see at this particular volume fraction, 0.52. That's sort of close to the melting transition. What you should see is that the orientations of the particles are aligned. So it is at least a liquid crystalline material. Now, is it a crystal? Well, I started this system with all the layers of the same color. So very quickly, these colors mix up completely, which tells you that the particles have a high mobility. They move almost like in the fluid phase. But is it a crystal? Well, it turns out that if you compute what are the average positions of these particles, they actually lie on a cubic lattice. So in some ways, it is a cubic lattice, a cubic crystal. But it's a very unusual crystal because the fluctuations around these average positions are liquid-like. They're unlike any solid you have seen. So what do you call this? After a while, we came to the idea that perhaps the taxonomy of these phases is not as important as just the recognition that this phase is very unusual. Right? You will not find a liquid crystal like this or a crystal that behaves like this. And we believe that somebody somewhere is going to find some very neat application to this unique phase. This is just to illustrate the idea that nowadays it's very easy to make particles of different shapes using different synthesis techniques, such as, for example, this modified polydispersity process that produces this so-called truncated cube family that goes from cubes all the way to octahedra. And for example, in this family, the cubes and the truncated octahedron are space filling, while the others are sort of near space filling. People can make them of different materials, of different sizes, and do a number of things with them. So this is just an example of some of the shapes that we studied. In fact, this family are all space-filling polyhedra, and it's showing on the one side that at low concentrations you have the boring isotropic phases. On this other side of the concentration spectrum you have the expected crystalline structures, but in the middle you oftentimes find these very interesting mesophases, like in the case of cubes. And let me show you. So this phase is for the truncated octahedron. And what you see now is that the particles do stay put in these lattice positions. You see that the layers maintain the colors, but in those positions the particles are rotating freely. That's why this is called a rotating phase or a plastic solid. And again, it's a very unusual, very beautiful system. There are, of course, many laboratories that have been playing with these particles and finding some of these phases. In chemical engineering, in Professor Handel's lab, there have been some instances where he, in fact, uses these nanodots that happen to have some of these shapes of these truncated cubes, and he wants to assemble them in some ordered ways because that affects the efficiency of the devices he's designing. And he has found a number of phases that actually resemble some of our crystal phases or mesophases. Now, is this a mesophase? Now, to begin talking about the methods that we use to be able to evaluate these properties, let's review the connection between thermodynamic states and free energies. So imagine that you are defining the state of the system by giving the temperature and the pressure. That we call an isobaric isothermal ensemble, or an entity ensemble for short, when we set up something like this. And if you were to map the phase space coordinates for this system, that means the set of all possible combinations of atomic positions and orientations and momentum, which is a highly dimensional space. Here I'm just drawing it in one dimension, right? Then you will find that each one of those combinations, we're going to call them microstates. That there will be a subset of these microstates, an ensemble of these microstates, that will be most likely to be visited given these conditions. And statistical mechanics tell us that the probability of any microstate I will be proportional to this sort of Boltzmann factor that depends on the temperature and the pressure field that we have imposed, but also depend on the energy and the volume of the given configuration R. So it may look something like this. Now if you take minus the logarithm of this little p, what you will produce is what can be referred to as a configuration of free energy. And now it will be something like this. You can see that this maximum now becomes a minimum because we are taking minus the log. Yeah, you may ask, what happened over here? No, I didn't see anything there. What happened? Well, just a matter of a scale. That when you're looking things at this scale, you see nothing, but you're taking the log scale and then some features appear. In this case, kind of illustrating that you may have multiple minima that may correspond to metastable states. Now let's simplify this a little bit. So let's consider cases where you have hard particles, so the potential energy will be always zero. And rather than trying to use this phase space coordinate, let's choose some coordinate that will be meaningful for this system, for example, the volume. And so this will transform to something like this. The same idea as before. Now I will say that you have a probability of macrostates. Now the volume is a macrostate in the sense that there are very many microstates that have the same volume V. Right? And that number is this omega, oftentimes called the density of states. And now the probability with this pi of me observing a volume V will be proportional not just to the normal Boltzmann factor that I showed you before, but also to the number of microstates that have that Boltzmann factor. It will be this. And again, if you take the minus the log of this pi, you will get this sort of dimensionless free energy function, oftentimes called a Landau free energy. That in this case, it's shown to illustrate that you may have a metastable basing of the band. Important to note is that there will be a significant contribution to this free energy that comes from this omega. Right? This is what we think about entropy. And also, of course, in the free energy barriers, there will be a contribution from this omega. Now, just a notation thing for later, that I'm going to associate to this sort of macro variable that is an extensive property, the symbol capital X for extensive, and to the field that you impose, in this case P over KT, F. Okay, so this is sort of a more general notation that will come handy in a moment. And so using that, you can also write the partition function, which is the thing that will normalize this quantity. Okay? Now this partition function, that's this integral, is related to the area under this curve. It's not the area, it's related to, it's proportional to it. And the free energy is just minus the log of this cube. So given some state, there's one number q, one number phi, different from this free energy, which is a function. That's a Landau free energy. So, and this is kind of what we saw in the case of the cubes that I was telling you about. So in this case, the field that I'm imposing may be pressure, right? This is the right parameter V. And so under these conditions, you may be observing the basing corresponding to the isotropic phase. And as you change the pressure, at some point, you see that the depths of these two wells become more or less the same. That we are going to call the ordered disordered transition pressure, or just ODP, shown here. And if you were to plot under those conditions, what's this probability of macrostates? It will be this bimodal distribution. Now, what that says is that you have equal chance to observe the system either under this hump or under this hump. The two areas are the same. And that, by definition, is phase coexistence, right? Phase equilibrium. And if you remember what I told you about the meaning of these areas, that also means that the partition functions associated to the two phases and the free energies are the same. So this should apply there. And if you keep going up in pressure, say, then the basin that used to be metastable now has become the stable phase that could be, say, this ordered phase for the cubes. Now you may ask, so is this a good way to find this phase coexistence? The conditions, this ODP say. And the answer is not really, because what's going to happen is that that if you are, say, under this condition, this ODP, you start the system with this isotropic state, the system will stay there, because there will be such a large free energy barrier that it will be really impossible to go over the other side. To really be able to sample both basins, you will have to have basically an ergodic sampling where the system can go back and forth between the two many times to be able to truly say that, that was the equilibrium condition, right? So, and likewise, if you were to do things from the other side, so basically taking this and expanding, going down in pressure, there will be significant hysteresis either way, compressing or expanding. So this will be the best method to find phase coexistence. At best, can give you a bracket of where this coexistence is going to happen. So now this allows me to sort of give you a sense for what some of the main challenges are in using these methods. So again, one of the key issues is whether you have the means to find these basins, right? And sometimes you have to go beyond Metropolis Monte Carlo to do it, use special techniques to do so. The other thing is that we'd like to pinpoint these conditions where phase coexistence happen, because those are usually the most interesting ones when phase transitions occur. Then in many cases you want to map out those free energies, especially when the order parameter you use there has a meaning in the context of the kinetics. It's a good reaction coordinate for, say, these order-disordered transitions. And of course also to get rates. Now for the remainder of this talk, I would only be able to give you one example of some of the methods that we use to find this phase transition. And let me illustrate that by giving you some results. Again, for the case of cubes that I already showed you. So I told you there's some ODP at which you have coexistence between the isotropic and this cubic mesophase. That's for the case of the monodispersed system. But as you know, experimentally, oftentimes you have polydispersity. And you may wonder, how does size polydispersity affect this equilibrium? Right? So you may have some kind of Gaussian distribution, say, of these particle sizes. It turns out that you need to use a very special ensemble that we call the semi-grand osmotic ensemble. And what is interesting about this is that you fix the pressure, temperature, you fix the total number of particles, but in principle you have an infinite number of species, because you're supposed to be sampling all possible sizes from this continuum distribution. So that makes this calculation a little bit interesting, but the only thing you need to remember is that there is a parameter, I'm going to call F1, that controls the width of this polydispersity. This S is given by the usual way how we define polydispersity. And for these results, I'm going to show different colors, where I will use these colors if the sizes are smaller than the average, and these colors if they are larger than the average. So I tune F so that I have a polydispersity of, say, 6%. And these are now the two phases that you form. You see, there's not much partitioning between the two phases. By the time you go to 12% polydispersity, you can see that this is now the isotropic distribution, this is the order distribution, and you can see that now many of the smaller components tend to partition into the isotropic phase, and a good fraction of the larger components tend to fractionate into this ordered phase. Now what's interesting is that there's a limiting value of polydispersity, which in this case is 12%. You cannot form this phase if your polydispersity is more than that. And that can be understood because if the disparity between the sizes is too much, they are not going to really be happy fitting into these cubic lattice, right? But this number is large if you compare this to hard spheres, where the same number is about 6%, much smaller. So that's very interesting, because if you think about it, polydispersity is promoting disorder, right? So how come these guys are able to resist this disordering effect much more than spheres? And we believe that that has to do with this sort of idea of entropic bonds. that the fact that they have these orientation correlations is helping the system stay in this ordered state. And in fact, we have tried these calculations for other particle shapes, and we always find that those space-filling polyhedra tend to be more resilient to the disordering effect of polydispersity. But I didn't tell you how I got phase coexistence, right? So I told you about this sort of freaky ensemble, but I didn't tell you how you got phase coexistence. So that could be explained in the following way, that again, going back to this free energy landscapes I showed you before, so this corresponds to phase coexistence for the monodispersed case, and this is what happens as you change, say, this parameter that changes the extent of polydispersity in the system. And in some way, we have mapped all these coexistence conditions where the free energies are the same between the two phases. So how do you do it? And I told you that just doing compression expansion runs is not the best way to do it. So what you need to do in these cases, especially when you have a solid phase involved, is that you need to relate the state of interest with the state of known free energy that can be known analytically. In the case of the, for example, a disordered phase, you can use the ideal gas state as this reference state and do a thermodynamic intervention and go from here to there to get the free energy. In the case of a solid phase, you need to use as reference system an ideal Einstein crystal, which is basically a set of classical harmonic oscillators. Now, going from here to there is in fact highly non-trivial. Right? So it involves a number of steps, and for a system like ours that has orientation in translational order, is in fact very tricky. But it's a relatively standard method, and we have used this, and in fact, it will take about from 20 to 40 different simulations just to be able to trace those paths. So it's an expensive, tedious calculation. Okay? And it's a kind of calculation that I don't want to be doing it if I change something else. Right? Maybe not just this other f, but other f's that I want to change, and repeating that every single time would be just too expensive. What I want is a method that allows me to walk from this state that I calculated expensively to these other states in an inexpensive way. Right? By doing that, I will basically be mapping out a set of values of f1 and f2 that correspond to these coexistence conditions. So this is the idea, that, for example, this is what controls the extent of polydispersity. F2 will be something like the osmotic pressure, and I want to trace this curve that corresponds to all those conditions where these two phases are coexisting, phase 1 and phase 2. It turns out that this sort of stepwise mapping is something that people have been doing for a while, and the key idea is that from this known starting point that you have calculated, you try to model some key function, so you model it via some suitable basis functions. And there are two methods that have been found to be very successful. One of them is known as the Gibbs-Duhem integration by Koch and co-workers, where the actual function they try to model is exactly this curve. So this relation between F2 and F1 of coexistence. And they derive this basically from just thermodynamics. From the fundamental equation, they're able to write this. So what they're proposing is that you can basically map out this by integrating this differential equation from some initial conditions, initial point, and you evaluate this side of the equation numerically based on simulation data. Now, this has been shown to be rather successful in many systems. The problem is that the way it's applied, it has no diagnostics for errors in the free energy. So you match the free energies there, but there is no guarantee that maybe the free energies start diverging as you keep integrating along this line. Okay, so that's an issue there. A method that has no such issue is known as the multi-histogram reweighting method. In this case, the key function they try to model is what's known as the density of state. This omega function I told you before, which now is going to depend on two extensive properties, x1 and x2. Right? Now, in this case, what you need to have is basically collect histograms for the different conditions that you impose F1 and F2. And this is an example where you see 3 histograms for 3 different points. For the method to work as designed, these histograms have to overlap. And the problem is that for the same conditions, if you make the system bigger and bigger, these histograms start overlapping less and less. that's known in the field as the curse of large system sizes. So if your system is small, you're happy. If it's very large, we need very, very many more steps to be able to cover some range of F1s. So there is that problem there. So what they wanted to have is a method that doesn't have these pitfalls. And in a sense, what they thought is maybe I can have something like this Gibbs-Duhem equation, but that takes care of phi, that is free energy. And what they thought is that maybe what I should use as the key function to model is the free energy itself, because then I can be sure whether I'm making errors in this free energy function. And sort of pictorially, what that means is that if you envision that the two phases, not 1 and 2, and these are the two external fields that define the ensemble, then each phase has its own surface of free energy, right? And the coexistence line corresponds to the intersection between these two surfaces. So what I want to model is what happens around this coexistence line in these surfaces. So I'm going to give you the key idea of how these methods work. Now, in this ensemble, I have two fields, F1 and F2, right? In the previous example, there may be one that controls polydispersity, the other one was osmotic pressure. This Y only controls the size of the system. Now, this formula is for the probability of macro states. Now, this pi I showed you before. In what I showed you before, you have just one X and one F. This is the same, but just for two X's and two F's. So remember, these X's are these quantities that fluctuate in the system. And this will be basically the histogram that you will produce in the simulation. But everything is the same. The definition of the partition function, again, is the same, just for two variables. And likewise, the free energy will be given by the same kind of equation. So using this, you can now apply equation. Well, remember, you know what's the free energy at conditions A. Let's suppose that A is the known point. So I am going to apply this equation at conditions A and B, and make a ratio of them, because by doing that, I will be able to get a ratio of the Q's, which is what I want. And moreover, that's going to eliminate omega, because omega, this density of state function, does not depend on the state of the system, doesn't depend on the F's. Right? So I eliminate that, and I can create a ratio of Q1 and QB and QA. I put all the exponentials on one side. That's why now you have these delta F's, which are just difference of F between B and A. And if I integrate and take logarithms, you will see that from this ratio I can get phi, because that's the definition of the free energy. And basically I just need to worry about this object, right? Now if you assume that this pi function, this probability of macro states, is a delta function, then this basically reduces to an expression that gives rise to the Gibbs-Duhem method that I showed you before. While if I use pi as a full histogram collected from simulations, then I have basically this single histogram reweighting method. Because I told you, these two methods have some issues, right? This method has, I guess, the advantage that you only need to know the averages of the X. Here you need to know all the probability functions. So what they thought is maybe a compromise is to assume that pi is a Gaussian function. In this case, it would be a Gaussian in two dimensions. And you will need to know not just the average of the x's, but also their covariances. But again, that's something that you can very easily get from the simulations by using the standard formulas. And if you use this formula here, this integration can be done analytically. What you end up, perhaps not surprisingly, is that this equation becomes this second-order Taylor expansion in the free energy around the state A, which remember is the known state. So it's a nice result. It doesn't mean that necessarily this is going to be a good extrapolator, but it gave me the idea that polynomial functions could be good ways to model the free energy, right? And this is where this method that I named the Phoenix method, or free energy extrapolation method, comes about. So the idea is that I'm going to use data for the averages and covariances of these X properties to model phi as this polynomial function. Remember that state A, I know everything. I will know the C's, know these coefficients. And then I write this for phase 1 and for phase 2, and they have to be equal, right, for phase coexistence. And I'm giving some step size. Right? So this is in the variable 1. So I know what's delta F1, but I don't know what's delta F2 for this new state B. But that's the only unknown in this equation. So I just need to solve this equation for delta F2 that produces the value of F2 at coexistence conditions at point B. So knowing that, then I can run simulations at this point B, and from those simulations I can collect data for the averages and the covariances of the X properties. And once I have that, I can now refine my estimations of these coefficients of the polynomial fit and the free energy differences, for example. This is an example of if I were to use a fourth order polynomial in this case, then this is the equation that it produces for the free energy difference between B and A. Notice the difference between this and the expression I showed you before. This was just a simple Taylor expansion around A. This expression uses information from both A and B, and hence it's much more accurate. And as far as we have tested it, it's extremely accurate in getting free energy differences. So once you have that, you can just relabel point B as point A and go back again, basically take another step and another step until you're finished covering the range of interest. And at the end, you can use all the data to make your best estimates for the coexistence properties for F and the X properties. And this is just to illustrate pictorially what I just said. I'm trying to map out this function. Remember that the first point is known by some method. I'm going to take a step delta F1, and I do an extrapolation starting from that point, may produce that point. Then I go there, I run simulations, collect these averages and covariances. That allows me to improve my estimation of the free energy calculation, and for example, to improve the predictions for the coexistence conditions. And I keep doing that as I move up in this curve. This is an example from this problem I show you for the polydispersed cubes. Here I'm showing the histograms for the property X2 that fluctuates, that relates to the size polydispersity. And it shows that these histograms have no overlap whatsoever. Right? So I couldn't use, for these step sizes, I couldn't use histogram reweighting. In fact, I'll have to use 5 times many more points in between to be able to really have overlapping histograms to use that method. This is only for 1,000 particles. Imagine if you have, say, 10,000 particles. So it makes these calculations much more efficient. But of course, there are a number of things that are still left out to optimize. For example, what's the best order of these polynomials to use? Should I use different kinds of basis functions for this model? And how you optimize this step size delta F1? So clearly you want to minimize not just the computational cost, but also minimize the statistical error in phi, and they usually sort of oppose each other. In our applications, I can calculate these quantities and make sure that I'm using a delta F1 step that produces very good efficiency, but it's still work to do to be able to come up with sort of rules or guidelines that can be applied to all systems in general. So there is certainly work to do there. In the last minutes, I just want to illustrate how I use this method in doing the following. I would like to design mixtures, basically new kinds of mixed states where using, say, 2 particle shapes, such that they have some interesting order. So let me first, because in some ways that's what you are supposed to do with chemistry, to create these very interesting compounds. So this is to illustrate what happens when the 2 pure components, maybe these are mixtures, are very different in the kinds of phases they form. In this case, spheres in cubes, and this is pressure scale, this is composition. You have pure spheres, you will go from an isotropic phase into this FCC phase at some ordinary disorder pressure, or dPa. And on this other side, we have pure cubes, you go from isotropic to this cubic mesophase at some ODP. Now, unfortunately, you cannot see the fact that everything in between here is gray. What it's supposed to show is that for any composition in between, you have never a solid solution. So basically, these guys will phase separate into basically a pure crystal of the spheres and a pure crystal of the solid. There are no solid solutions. The only condition when they mix is when the concentrations are low enough that they form a mesotropic phase. So I want to optimize this solid phase solubility. Now, this is entropy. I mean, these are just hard particles, and hence the packing is going to play an important role, meaning that the relative sizes I choose for these particles is going to be crucial. These results happen when the sphere radius is equal to the cube circumradius. So let's change that. And if you change it for the case when the sphere diameter equal to the cube side, so equal in radius, now this happens. And all of a sudden, you have opened up this region in this phase diagram where you have this solid solution, where you have basically a cube-rich cubic phase that contains up to 20% of these hard spheres. It's really cool, it's really nice. But can we optimize this further? Because on this other side, there's nothing. So the spheres don't want to have nothing to do with cubes. There's no solid solution there. So this idea of trying to optimize the co-assembly, this is entropy-driven assembly. Well, one way to think about this is as follows. So in this case, the ODPs of the pure components are very different, right? And say for any pressure in between this ODP and that ODP, say this with a red line, under these conditions, the cubes are more than ready to order. The spheres are not. They couldn't care less. It's almost like having a couple that are sort of talking about getting married, but only one of them is ready to commit. So this matrimony is not going to work. Only one partner is trying. The same thing here. So what you need to have is both partners being equally ready to this change in a situation where you go from disorder to order. So what if I choose sizes such that the ODPs of the two species are the same? So we synchronize the conditions where packing entropy becomes dominant. And that happens when the sphere diameter is 23% bigger than the side of the cube. And what you see now is this, where on this side, it's basically the same as what I showed you before, but now on this side, notice that this whole area has opened up, where now you have a solid solution, where in the sphere-rich FCC phase, you can dissolve up to 20% of cubes, which is rather remarkable when you think about how different these cubic lattices are. So we have synchronized packing entropy dominance, and if you do some calculations based on thermodynamics, you can show that when this happens, the packing entropy per particle, if you look at this phase here, and this phase there, you calculate the packing entropy per particle is the same. So in some way, what you're doing is that if they want to exchange species, particles from one phase to the other, you're minimizing the free energy cost of this exchange. So you are giving them the best possible chance to pack, because you are basically making compatible the packing entropy of the two species. Now, in this case, it's impossible to form anything, say, at concentrations of 50%. But what will happen if now you are using particle shapes whose solid phases are a little bit more similar? So we have tried that. Let's have just 3 examples where now they are more similar, and what you find is that, in fact, now they can form a solid phase solution that happens for all compositions. These are shown as these regions here in yellow, and in fact, under those conditions, the system is a mesophase, it's a rotator phase, like the one I showed you before. So this seems to be a very general rule. Well, how about compounds? For example, can I make this compact? We will like a one-to-one sodium chloride phase, which is kind of like, say, making compounds of this salt, where you have, in this case, these two species that are from this tessellating structure. In my mind, being able to do these things with these particles is like being able to make zeolites or make some of these fancy salts that people are using now for solar cells. Can we make these compounds? Well, in this case, the answer seems to be no. We cannot do this using entropy alone. And in this case, the answer seems to be not kinetic. It's too difficult. So what shall we do? Well, let's try energy. Now, some of you may say, hey, that's cheating. You said that entropy was bad. I never said that. What I said is that what is bad is to only focus on energy and basically forget about entropy. So if I'm going to use energy, how will I do it? Well, just by looking at these structures, you can tell that what you need to favor is the cross interaction between different species, in this case between spheres and cubes, as opposed to the like species. So just make those cross interactions more favorable. And that leads to my third aphorism that says that energy is easier to design than entropy, at least conceptually. Not saying that's easy to do, maybe very hard, but it's easier to imagine, I guess. There are different ways how you can implement selective interactions. You can use ionic interactions, or an approach that's very popular nowadays is by using this DNA hybridization. So you attach ligands to the particles, and given the complementarity of these strands, you can tune the strength of these attractions. And in fact, this is something that very recently has been done in the Brookhaven laboratory for spheres and cubes, exactly the same system I was dealing with. They have shown that they can form, in fact, this superlattice structure. Now, what we are finding now is that if you use the optimal size ratio of these particles I showed you before, so this is the optimal entropic size ratio, then you can use the smallest energy bias, which is nice, which is good. It sort of makes sense because by doing that, you're fighting entropy the least, right? So which makes sense. So with that, I just want to mention that there are these other challenges in methods that we have also done a lot referring to the kinetics of the systems. We'll not really have time to do that, but just to emphasize the importance of doing these things, because it doesn't matter if you show that you can form this very interesting phase or mesophase if it's going to take forever to realize it in the laboratory. So we need to identify sort of fast assemblies. And we have done so. In fact, we have some results for that where we can actually show that these systems assemble very fast. This is just a movie for this truncated octahedron that is going to go from the isotropic phase to the rotator phase. And we have methods that would allow us to compute the rates. And we can tell you that, oh, the rates are much faster than crystallizing, say, hard spheres. Which is much harder to do is to understand why. There is something going on in the isotropic phase that's making these entropic Fresnel barriers to be much smaller. So it's a long story, but we think that it has to do with this sort of productive fluctuations in these orientations produced by these entropic bonds. So with that, I just want to conclude by saying that there are a number of challenges as far as the methods that are needed to study these systems. I will not read this, just to tell you that we are trying to identify some of these rules for the productive assembly in binary systems for mixtures and compounds. But if there is a message that I want to convey is the following, that maybe for some systems, we should shift to a new paradigm where we try to co-engineer entropy and enthalpic effects. And possibly one should be designing entropy first, because in that manner, you make sure that you are not going to be fighting entropy, but entropy will be on your side in as much as it's possible. And that can lead to more robust designs and behaviors. There's, of course, many more things to do with the systems as far as modeling, but I just want to conclude by giving you my fourth aphorism that says that high complexity and order, and to my eyes anyways, beauty, have arisen in nature, not despite of entropy, but really thanks to entropy. And if I'm going to thank entropy, let me thank you for your attention. I'm happy to take any time.
So, kinetics, like how do we deal with the kinetics part, just like the stuff that we've been talking about? Do you have ideas of going forward in terms of if you're starting in one metastable state, how do you overcome the energy barriers to get to your ground, your global equilibrium, things like that?
Yeah, so I mean, it's really another whole talk that's exclusively devoted to kinetics. And we have no methods that we have developed and optimized to be able to do these nucleation experiments. And what we are doing now is sort of basically going through different shapes and measuring the rates, measuring free energy barriers. And even though you can quantify these things, but as I mentioned before, it's not so trivial to understand why sometimes something is faster than, say, hard spheres. Now, I mentioned in this example that we initially expected that the rates of this process would be similar to hard spheres for the same degree of supersaturation, right? Because in both cases, you have these sort of rounded objects that are forming a phase that has translational order. In one case, FCC, in this case, something a little different. And yet we find that in this case, it's much faster. Now, there are other shapes where it's much slower. And you can measure it, but making sense of that has to do with really making sense to what happens in the isotropic phase. I think that, like, maybe if you think like this, but initially I thought that, the isotropic phase is completely stupid and boring. There's nothing going on. Everybody just having a walk. But in reality, all the interesting physics seem to be happening there. If you identify, in this case, for example, fluctuations in orientational order, in translational order, they happen locally. So we're not talking about globally, but just locally. The fluctuations are happening all the time. And the reason you see different colors here is because we are trying to identify those pockets where you have more order of alignment of the particles, or more order in the sense of the symmetry of the particles around them. And what we find is that sometimes these fluctuations of translational and orientational order are productive, so they are synergistic. They are sort of helping each other, and that's apparently lowering this free energy of the barrier for the ordering. But in some other systems, they seem to fight, and when that happens, then the barriers are higher. So again, I'm using hard spheres as a reference because there will be the baseline system. But so we're still in the process of understanding that. So we have some stories, partial stories that we understand but not completely.
So are there situations in which you can actually rule out certain phase behaviors? For example, when you were looking at the solid-solid solutions, and you were trying to get solid-solid solutions on both sides of in both extremes of concentrations.
Yes.
So it seemed very creative. You got a sense of what you could do at one side, and maybe how to do it in the other. But it all seemed a little bit empirical. Are there situations where you can actually rule things out, or kind of give theorems that say this can't happen now or this can't happen?
Yeah, so I mean, in this system, my theorem, which I didn't realize a priori, was, so I didn't know what size ratios to use. Right? So I said there may be a size ratio that optimizes the solid phase miscibility. Had I been smarter, or my student was smarter as well, maybe I could have said, what if I choose sizes such that in the crystalline phases, they have the same entropy per particle? Had I done that, then I would have found that happens when the ODPs are the same for the two systems. And sure enough, that produces this. But in practice, what we did is basically try different sizes. We use our Phoenix method that allows us to map out these phase diagrams very quickly. And it's from the analysis of this data that we made sense that, and of course, once you think about it, you say, of course, that should have been the case, because bulking entropy is what it's really controlling these transitions. Right?
And
so
that discovered knowledge ports over to other systems as well?
We have taken this idea to other systems, and it works really well, even when the systems are very different, very disparate. Yes.
So sort of following on that, is it interesting that the 1.23 corresponds to the half diameter or the half diagonal of the cube?
I mean, in this case, there may be some...
So that it would allow precise rotation of the cube and exactly the space that a sphere could rotate?
No, but it's not circumscribed or...
I know, but it's 1.23. That's exactly when it happens. And that is, if you make that the half size, and you compute the diameter.
There is something,
of the
I
cube,
guess,
exactly that.
here, but how about there? I'm not sure in that phase that has...
I mean, that's exactly the size of that's exactly the length of the diameter of the cube, corresponding to that size.
Interesting.
Yeah, so I think that in this case, anyways, you can, and I think that's true for any pair that you analyze. At the end, this entropy considerations are arising from the geometry, right? And you will find that, yeah, there's something that makes sense as far as what the geometry should be. I should mention that that number is very forgiving in the sense that you can be from 17 all the way to 1.3, you almost get the same thing. So it's not like, oh, you have to be exact at that ratio to have this. So you have this broad plateau of ratios that will allow you to have this sort of maximum solid phase visibility. But I see your point that there is something about the geometry that maybe a priori can help you guide this calculation.
You could allow local melting, right?
Further questions? So let's thank Fernando again. We have some refreshments just down the hall.